Swayam Prabha. Digital India. Educated India.
Welcome back to the video lecture on fluid mechanics. So, in the last lecture we were discussing about the fluid statics, we were discussing about the forces on solids and then say the applications of theories from solid mechanics, and we have started with the static fluids theories like on a fluid element rest. We have seen that the equation sigma fx is equal to 0, sigma fi is equal to 0, sigma fz is equal to 0. That means some of the forces in x, y, z directions equal to 0 as we use in solid mechanics. So, similarly, the sum of moments of forces sigma mx is equal to 0, that also we have seen, and we have defined the pressure, and also we have seen the applications of Pascal law for pressure at any point. So, as we have seen, as per the Pascal law, pressure at any point is same in all directions. So, that derivations also we have seen in the last lecture, and also we have seen the pressure variation vertical direction and also in horizontal direction. And as we have seen in the last lecture, say the pressure intensity of fluid is independent of shape. So, as you can see here, it is same on this x-axis line, and then we have seen the applications of the concept of force versus area. Say here, as we have discussed in the last lecture, say here force F1 on this side is P into A1, and on other side F2 is equal to P into A2. Since P is same on both, say the pressure intensity at level P and Q, Pp is equal to PQ. So, transmission of pressure through the stationary fluid is have a large number of applications in many practical engineering areas, like in use of hydraulic jacks, presses, etc. So, here you can see that the force applied F1 is on this side is equal to P into A1, which with a small force we can rise or we can get a large force back. F2 is equal to P into A2. So, these applications, like as I mentioned, the hydraulic jacks or lifts, presses, etc. are very much used in engineering areas. So, now just one application here you can see, a man can lift the car. So, here a car is placed on this side, and here a small cylinder, a man is standing, and then you can see just with his weight, due to the application of this principle, the car is lifting. So, that is very much obvious from this animation. So, what is happening is the pressure intensity is same on both sides, but here the area is smaller. So, with respect to that, P into A1 is much smaller force. So, using that we can rise this P into A2, which is a very large force. So, that this car is raised as shown in this animation. So, now we will discuss the general equation for pressure variation in a static fluid. So, for this purpose we will just consider, as shown in this slide, you can see here we consider a fluid element, a cylindrical element of fluid at an arbitrary orientation like this we will consider. So, on this face of the cylinder, the fluid cylinder, say the pressure, the force is P into, if the pressure intensity is P, force is equal to P into A, and on the other side say it is, if the pressure is increasing delta P by delta P, then on this side the force is equal to P plus delta P into A. So, here for this fluid, the fluid density is rho, and now here say this distance is Z, and here Z plus delta Z. So, the force acting on the element R, P into A, acting at right angles to the end of the face at Z, this as shown here, and on the other side P plus delta A acting at right angle to the end of the cylinder element at Z plus delta Z, and then there will be the weight of the element, that will be mg. So, now we consider all this using the Newton's second law. We can write P into A minus P plus delta P into A minus rho g A into delta Z cos theta is equal to 0 if we consider this direction. So, that using the Newton's second law, that means force is equal to say the total mass into acceleration. So, here with respect to this we can get at equilibrium of the element, the result force in any direction is 0, as we have seen in the case of static fluids. So, using that principle we will get delta P is equal to minus rho g into delta S cos theta, or we get delta P by delta S is equal to minus rho g cos theta, as this theta is this angle with respect to this inclination, with respect to the vertical, theta is with respect to vertical. So, finally, we get a general expression dP by ds is equal to minus rho g cos theta as shown here. So, theta is this angle, g is the acceleration due to gravity, and rho is the density of the fluid. So, this equation gives the general equation for pressure variation in static fluid. So, now we have considered an inclined element or cylindrical fluid element like this. So, with respect to this equation we can write the general equation for any type of, say, whether horizontal, vertical or inclined type pressure variation in static fluids. So, now with respect to the general equation which we have derived now, if theta is equal to 90, then the on horizontal plane we can see that dP by ds as theta equal to 90 is equal to dP by dx, that is equal to dP by dy, that is equal to 0. And with respect to earlier figure, if theta is equal to 0, that means the plane is vertical. So, for a vertical plane like this, so then dP by ds is equal to minus rho into g. So, here you can see that this is a small basin where we have stored some water. So, in the horizontal plane you can see that the pressure is 0, and in the vertical plane we can see that the pressure when theta is equal to 0, dP by ds is equal to minus rho g, and here this P, the pressure intensity, is a function of Z only, or we can write dP is equal to minus rho g dz, or where rho g is equal to the specific weight. So, that we can write dP is equal to minus gamma dz. So, this gives the general equation for pressure variation in static fluid. So, now we will briefly discuss the relations between the pressure and head. So, for that purpose let us consider, say, a small basin of fluid, or say here water as shown here. So, now this fluid, this is in static condition. So, the pressure on the surface is atmospheric pressure. So, as here as shown in this figure, we can write P is equal to rho into GH and plus constant, that means if any other than atmospheric pressure. So, generally atmospheric pressure can be considered 0. So, that P is equal to rho g into H. So, but if we consider the atmospheric pressure, then total pressure is equal to pressure intensity is equal to rho GH plus P atmosphere. So, this gives a relationship between the pressure and the head as shown in this slide. So, if we consider the atmospheric pressure as datum, then we can say that the pressure above or below atmosphere, that pressure is called the gauge pressure. So, if we consider the atmospheric pressure as 0, or that is the datum, then we can define the gauge pressure as the pressure above or below atmospheric pressure. So that the P gauge or the gauge pressure is equal to rho into GH, as we have seen the previous slide. So, as we know, the lower limit of any pressure is 0 for the case of perfect vacuum, or if we consider as datum, then pressure measured above this datum is called the absolute pressure. So, when we consider, we can classify the pressure into the absolute pressure or gauge pressure. So, the gauge pressure is the pressure above or below the atmospheric pressure. So, that the equation is P gauge is equal to rho into GH, and absolute pressure is defined as absolute pressure is equal to gauge pressure plus atmospheric pressure or the datum which we are based on. So, absolute pressure is equal to gauge pressure plus the atmospheric pressure. So, now with respect to this, say when we consider the various pressure like gauge pressure or absolute pressure or atmospheric pressure, let us consider in this slide. As you can see, if this is the absolute 0 reference as far as the pressure measurement is concerned. So, if we consider say here this particular point say 1, then we are measuring as absolute pressure, and if this line indicates the local atmospheric pressure reference, then with respect to that, when we measure the pressure at this particular point, then it is called the gauge pressure. But when we are measuring with respect to the atmospheric pressure and the gauge pressure together, that pressure is the absolute pressure. So, we can differentiate the pressure measurement with respect to either we are using the gauge pressure or the absolute pressure as shown in this slide. So, now we will further discuss about the pressure variation. So, the pressure variation for incompressible fluid. So, you can see that say with as we have seen in the previous slides, it is say rho g or gamma into dz. So, if we consider say from one point to another in the vertical direction, so we can just integrate this total to get the total pressure variation. We can just integrate gamma z dz. So, generally say we have to use a sign convention, whether say the pressure above the atmospheric, whether it is positive or negative. So, we can consider say we can put it whether it is increasing or decreasing direction as positive or negative as shown here. So, finally, if you integrate as we have seen in the previous slide, we get P is equal to gamma into Z. So, this we can measure using a manometer like this. The pressure variation can be measured say at a particular point at A we can measure the pressure. So, we will be discussing about the pressure measurements the later parts of this lecture. So, now we have seen the pressure can be say the gauge pressure or absolute pressure and then the atmospheric pressure. So, 1 atmosphere the pressure is defined as say 760 millimeter of mercury, or it is equal to 101.3 kilopascal, or again that is equivalent to 10.34 meter of water column. So, the atmospheric pressure is generally say expressed as say either 76 centimeter of mercury or 101.3 kilopascal or 10.34 meter of water column. So, these equations give the general pressure variation, and then with respect to the atmospheric pressure the values are these values given here. So, now with respect to the pressure variation we will demonstrate or we will discuss a small problem here. So, here the problem is, the problem statement is say first example say 2 kilometer away from the seashore at a spot the sea can be considered to be in 3 layers of 100 meter, 200 meter and 300 meter depth of salt water with specific gravity values of salt water in each of the constant density layers as 1.01, 1.02 and 1.03 respectively. So, assuming atmospheric pressure at the sea surface as 0, determine the pressure at the interface. So, here this I will demonstrate this problem with respect to this figure here. So, here you can see say if the seashore is on this side, we are considering 2 kilometer away from the seashore, at a particular spot. Here you can see 3 layers. So, first layer is about 100 meter and second layer is 200 meter and third layer is 300 meter, and this is the sea bed or sea bottom. So, now the atmospheric pressure can be considered as 0, and at this particular spot the specific gravity values of salt water in each of the constant density layers are given. For the first layer the density is 1.01, the second layer the density is 1.02, and the third layer the density is 1.03. So, we have to determine the pressure at the various interface. You can see here there is one interface and here the second interface, and here below at this position also we have to determine the pressure. So, we can just utilize the equation which we have derived earlier. So, the solution here you can see, say P1, we want to determine this P1, the pressure at this interface. So, that will be equal to the surface pressure, the atmospheric pressure here, P1 is equal to P0, which is the atmospheric pressure, plus rho 1 g, rho 1 is the density and g is the acceleration due to gravity. So, that gives the specific weight of the liquid at this layer. So, rho 1 into g, this depth is 100 meter. So, 100 if we are measuring the depth from the surface. So, this is at this particular position where we are measuring the P1, it will be P1 will be at this location. So, that will be obtained as P1 is equal to P0 plus rho 1 into g into 100 minus 0. So, since the depth is 100 meters, so this location P1 is equal to P0 plus rho 1 into g, rho 1 g is the specific weight into 100 minus 0, since we are measuring the datum as on the surface. So, from there only we are measuring. So, that is equal to, since atmospheric pressure as per the problem it is assumed as P0 is equal to 0. So, 0 plus, so S1 into rho g into 100. So, here it is given as 1.01 as the specific gravity of the first layer or the constant density layer as 1.01. So, g is 9.81 into 1.01. So, finally, multiplied by 100 we get 990.8 kilopascal. So, here at this location the pressure will be 990.8 kilopascal. So, similarly, now we will determine the pressure at position, say here this interface of between layer 2 and 3. So, that this location. So, P2 is equal to, here this location the pressure will be the pressure with respect to the top layer P1, that we have to add plus the specific gravity or the specific weight of this liquid in this layer. So, that is given as rho 2 into g. So, that is the specific weight with respect to this layer, and then multiply with respect to this layer thickness. So, that is equal to the total distance from the surface to the bottom of this layer is 300 meter. So, 300 minus 100 meter is the depth of the first layer. So, rho 2 g into 300 minus 100. So, that is equal to P1 plus S2 rho into g, where the S2 is the specific gravity of the constant density layer of the second layer is 1.02. So, rho is 1.02 multiplied by g 9.81 into 200. So, this gives the total pressure at this, say the interface between layer 2 and layer 3. So, that total P2 is equal to P1 we have already determined as 990.8 kilopascal, that plus this, say here this equal to S2 into rho g is about 10. So, 10 into 200. So, total pressure at this location will be P2 location here will be 2990.8 kilopascal. So, at this location the pressure will be 2990.8 kilopascal. So, similarly, now we will determine the pressure at this bottom of the sea. So, P3 is equal to the total pressure at this layer, two layer, first layer and second layer, that is all determined as P2. So, P2 plus this, say layer thickness total sea depth is say 600 meters. So, up to here is 300 meters. So, 600 minus 300. So, this depth will be 300 meter. So, to determine this pressure here, so P2 plus rho 3 into g or into S3, S3 is given as 1.03. So, that multiplied by this depth 300. So, that is equal to the previous P2 we have already determined as 2990.8, that plus this value is 10.104 into 300. So, that gives 6022 kilopascal. So, the pressure at the bottom of the sea at this location will be 6022 kilopascal, and the interface between layer 2 and layer 3 will be 2990.8 kilopascal, and between layer 1 and 2 P1 will be 990.8 kilopascal. So, using the general equation which we have derived earlier, we can determine the pressure variation like we have illustrated in this particular problem. So, now we will go to the next topic is pressure measurement. So, pressure measurement, especially fluid mechanics, is very important, since say various pressure is one of the most important fluid property. So, we have to determine the pressure in various cases, especially when we consider any kind of fluid flow problem, whether it is static or dynamics. But now we will be discussing fluid statics. So, here we will be discussing how to determine the pressure, or how we can measure the pressure for various cases. So, various types of equipments or various types of gauges are available for measurements. So, first one is called a mercury barometer. So, here you can see in this slide. So, the mercury barometer, the pressure is measured, especially this mercury barometer is used for pressure atmospheric pressure measurement. So, you can see that the pressure will be varying from, say, at sea level it will be say it will be maximum, and then it will be reducing, say, on the top of a mountain. So, we have to measure the atmospheric pressure at various levels or various position. So, we can use a mercury barometer like this. So, here say on a small basin the mercury is placed, and then a small tube you can see. So, here using this mercury barometer, here the mercury is used. So, the atmospheric pressure is measured as this gamma, this depth gamma multiplied by the specific weight gamma multiplied by this height h, gamma h plus if any vapor pressure, that gives the atmospheric pressure using a mercury barometer. So, this is the way which we will be generally measuring the atmospheric pressure. So, now we will discuss some other pressure measuring equipment. So, one of the simple most pressure measuring equipment is called a piezometer tube. So, here you can see, say if we want to measure the pressure in a pipe like this, or in a tank, or the position where we want, we can introduce a small piezometer tube. So, a piezometer is just like a tube where we can introduce it on particular location. So, this small tube, this is called a piezometer, and then this can be connected to various locations, like if you want to measure the pressure in a pipe, then you can just put like this. So, finally, we will be determine the water column, the height here, and then with respect to the equation which we have derived earlier, we can get or we can measure the pressure. So, as illustrated in this slide, so using a simple piezometer, a piezometer is connected here, and then it is open to the atmosphere. So, the depth is the rise due to the pressure in this pipe or the container. There will be a rise in pressure or rise in water column or liquid column, water or whatever the kind of liquid which you are considering. There will be a rise in liquid column here, that is H1 here, and then the piezometer, from the piezometer we can determine the pressure P as gamma into H plus P0, where P0 is the reference pressure. Say for example, if it is open, then it can be atmospheric pressure, which can be considered as 0, and pressure measured is the gauge pressure. So, here we are measuring the gauge pressure. So, this is the piezometer can be used in many cases, like especially for liquids. So, the disadvantage of piezometer is that we cannot measure too small pressure it is difficult to measure, or when the pressure is very large we cannot measure. So, that are the disadvantage of this piezometer, but the advantage is that it is very simple. We can directly connect to any pipe or container or any system and then see the pressure at that particular location as demonstrated in this slide. So, the pressure measurement using piezometer, we are just using the simple equation, and what we are getting is the gauge pressure. So, as we have seen, this use of say the piezometer has some disadvantages. We cannot measure the pressure very accurately, it cannot give say small variations in pressure, or even it cannot measure large pressure. So, one of the another type of equipment we generally use in laboratories and other places is called a U-tube manometer. So, the pressure measurement using U-tube manometer. So, here the fluid whose pressure is to be measured, say you can see that here a U-tube like tube shaped in U shape, and then there will be a manometric fluid inside in this U-tube. So, you can see here this is the manometric fluid of density rho manometer. So, here you can see, and then generally it will be a dense fluid, and then what we will be doing is where we have to measure the pressure accurately, we can connect this U-tube like this. So, here we are measuring the pressure in this pipe or a container like this. So, we are connecting this U-tube like this. So, with respect to the, since due to the pressure in this pipe or the container, say the liquid in the manometer liquid in this manometer U-tube manometer will be rising like this. So, now with respect to this we will be measuring generally this rise H2 and also this variation H1 we will be measuring using scales, the connected scales. So, from the principles that say the pressure at this location B and C should be same. So, if you use that principle, Pb is equal to Pc as shown in this slide. So, here with respect to this we can write Pb is equal to Pa, that means the pressure here, Pa plus rho into G, that means if rho is the density of fluid in this pipe. So, rho into G, G is the acceleration due to gravity. So, rho into G into H1. So, that gives the pressure at this particular location B, Pb. So, that is with respect to Pa. So, that Pb is equal to Pa plus rho G H1. So, similarly, we can find the pressure at the location C, that is obtained as Pc is equal to there will be, since here the manometer is open to atmosphere. So, this we have to consider the atmosphere pressure. If you are neglecting or if you are considering it as 0, then we do not have to consider, but here if you consider P atmospheric, then Pc is equal to P atmospheric plus the rho manometer, that the density of the manometer liquid multiplied by G into H2, this height of liquid which we are measuring. So, Pc is equal to P atmospheric plus rho manometer into G into H2. So, now our aim is to measure the pressure at this particular location here, this point A. So, to measure the pressure at this particular location A, we can use this principle P B is equal to Pc. If you get this, then we will get, and if we assume P atmospheric is equal to 0, then we get the pressure is equal to the density of the manometer liquid multiplied by G, the acceleration due to gravity, and this depth H2 which we measured, and then minus rho into, rho is the density of the fluid in the pipe, rho into acceleration due to gravity multiplied by this depth H1. So, this gives the pressure Pa, that means the pressure at point A. Pressure at point A is equal to rho in manometer G into H2 minus rho into G into H1. So, the basic principle of manometer here is, you can see that here we have just a U type pipe like this. So, here we put some liquid, either it can be mercury or any kind of liquid, and then we can connect this through another pipe where we have to measure the pressure. So, this is the point where we will be measuring. So, this is the simple principle used the case of manometer. So, now the pressure measurement using the manometer we can use it in different ways. So, first one is we have seen the last slide. So, just only one limb of the manometer is connected to a particular location where we want to measure the pressure, and now if you want to measure the pressure differentially, that means between two positions, say here A and B. So, for that we can use, when we use this manometer U2 manometer, it is called the differential U2 manometer. So, here we are determining the pressure at the pressure difference between A, here this location A and this location B. So, the one limb of the U2 manometer is connected to the pipe flow or the container here through a bent pipe like this, and other limb of the manometer is connected to the second pipe or the container at, say, with respect to this location B. So, now if there is a pressure difference between A and B, that means between the positions of this pipe and the second pipe, then we can write the equation as PA, the pressure at this location PA. We can, using scales, we can measure this depth H1 here as shown in this figure, and also we can measure this depth H2 here, say where the manometer liquid is raised. So, this is H2, and then we can measure this depth H3 with respect to this point B. So, this H3 can be also measured. So, finally, we can write the equation as PA plus gamma 1 H1 minus gamma 2 H2 minus gamma 3 H3 is equal to PB. So, this is the equation which we use for the differential U2 manometer. So, since we know the specific weight or the density of the liquid in this pipe, first pipe, and we also know the specific weight or the density of the manometer liquid, and then we also know the density of the specific weight of or in pipe 2 or for this container. So, say with respect to this H1, H2, H3 are already measured. So, we can get the pressure difference between A and B using this equation. So, if there is the same pipeline, if you want to measure the pressure between this position and the earlier position, that means between A and B here, we can see, say the fluid density is same. So, we can connect the manometer, both limbs like this, say first limb can be connected to this location and second limb can be connected to the second location, and then this difference can be H1, H2, H3 can be measured as in the previous case, and then finally, this equation can be used to get the pressure difference between points A and B as demonstrated in this figure. So, now using the manometer, U2 manometer, we have seen how to measure the pressure at a particular location as say here in the previous slide, and then again we have seen here, say here at a particular point if you want to measure the pressure. So, this shows the slide shows how we are doing, and then the second case we have seen, if you want to measure the pressure difference between two points or between say two pipelines or between two containers or between two locations, any type of locations, we can use the manometer like this, or in a single pipeline with the pressure difference between 2 points can be measured like this by connecting the two limbs of the manometer at two locations where we want to measure the pressure difference, and then we can use this PA, if the points are A and B, then PA plus gamma 1 H1 minus gamma 2 H2 minus gamma 3 H3 is equal to PB, where gamma 1 is the specific weight of first pipe, gamma 2 is the specific weight of the manometer liquid, and gamma 3 is the specific weight of the fluid in the second pipe. So, now you can see that using the manometer, the major difficulty here is that we have to do so many measurements. So, here say we have to measure to see the pressure difference, 3 measurements we have to do, P, H1, H2 and H3. So, if the measurements are not very accurate, then it will be the results will not be accurate. So, and moreover so many measurements are not good while determining the pressure very accurately. So, to deal with this kind of problems, say if you consider a manometer or this a mechanism like this, so where the diameter D is much larger compared to the diameter d on this limb. So, this diameter is small d. So, if d by d is very smaller, then we can say that with respect to this, say if you measure this Z2 is measured, then between this P1 and if we want to measure the pressure difference between P1 and P2, then we can with respect to this figure we can write the equation P1 minus, if since d by d is very small. So, if it is really smaller, d by d is smaller, then we can write the pressure difference as P1 minus P2 is equal to rho g into Z2. So, in this case we are measuring only at this location only, Z2 is only measured, and the equation is P1 minus P2 equal to rho g into Z2. So, the advantage is only one measurement, but it is less accurate than what we have seen in the earlier cases. And also say you can sometimes we can use the inclined or tilted manometer. So, that may be more accurate compared to the earlier one, which we say the inclined or tilted manometer is demonstrated in this figure here. So, you can see here, say now if you want to measure the pressure, say P1 here, and then if the pressure here is P2, then it is an inclined pipe with a manometric liquid like this. So, with respect to this figure, we can write the equation as the pressure difference is P1 minus P2 is the rho g Z2, that is equal to, so you can measure using a scale like this. So, that is equal to rho g x sin theta, where theta is this angle and x is the measured distance with using this scale here. So, that is called a inclined manometer, or we can also have a tilted type of manometer like this. So, where we are connected this manometer to pipes at location A and B, and then P A minus P B will be, if this L2 is this distance measured say between this level and this level, and gamma 2 is the specific weight of the manometric liquid inside, and then P A minus P B is equal to gamma 2 L2 sin theta with respect to this figure. So, this kind of inclined or tilted manometers are useful to measure very small pressure or the pressure difference. So, it is better than the previous one which we have discussed, since it can measure to more accuracy compared to the earlier one. So, now this manometer can be used for many applications. Say one of the generally used application is the pressure measurement by medical doctors. So, medical doctors use the manometer for blood pressure measurement. So, everybody, all of you have experienced this, how they are measuring the pressure, the doctors are measuring the blood pressure. So, what they are doing is a cuff is placed around arm and then inflated to a pressure above pressure in arm artery. So, and then slowly deflated, you can see that using some mechanism they are inflating or deflating in the arm artery, and slowly deflated reading attached mercury manometer to give peak, and peak is called systolic and the lowest is called diastolic pressure in millimeter of mercury. So, here also a manometer is used which gives the pressure, and this also you can see that it is a small U-tube type manometer. So, and also this manometer we can use in many kinds of say especially in laboratories we generally use manometer for pressure measurement, but nowadays this manometer, since we have to measure it using scales, and then the accuracy may not be to the level which we require in many of the sophisticated problems. So, then we will be using for say we will be going for mechanical type or other kinds of manometer. So, say like gauges. So, that we will be discussing in the next slide. So, before that let us see the major advantage of this manometer. So, manometric measurement, the advantage is it is very simple, there is no need of calibration. It can just say if there is a U-tube with a manometric liquid, we can just connect to the location where we want, and then that will just using a scale you can measure the height, and that will give directly the pressure or the pressure difference. So, it is very simple and no need of calibration. But some of the disadvantages here are, say the slow responsivity, if you want to measure the response using a manometer is very slow, and then it is very difficult to measure small variations. If there is with respect to a small temperature rise, if there is a small rise in pressure, these kinds of differences it is very difficult to observe using a manometer. And also it is not so accurate, since we will be measuring it using a scale, so the accuracy is also less, and say we have to do say as we have seen 2-3 times, we have to use a scale and then measure the heights, and then we have to use the equation. So these are some of the disadvantages of this manometer type of pressure measurement. Now we will discuss a problem for a differential manometer, how we can use a differential manometer, how we are getting the pressure. So in this problem, here in this figure you can see here the problem. So the problem is, say in figure the liquids at P and Q are water, and the liquid in the manometer is oil. So here there is a manometer, you can see it is just like a U2 manometer in the other direction, in the inverse position. So we want to measure the pressure at P and Q. This is two pipelines going in parallel. So at P we want to measure the pressure, which is the pipe P is containing water and pipe Q also containing water. So we want to measure the pressure difference between P and Q. So the water and the liquid in the manometer is the water is there in the pipes, and the liquid in the manometer is oil with a specific gravity of 0.9, and the readings in the measurements H1 is equal to, so here H1 is equal to 300 millimeter and H2 is equal to 200 millimeter, and this H3 is measured as 700 millimeter. We have to find the pressure difference in pascals. So to solve this problem, so now already we know this H1, H2 and H3, and we want to find the pressure difference between P and Q in Pascal, and then the density or the specific gravity of oil in the manometer is also given. So with respect to this figure, we can write the pressure, say at location P can be written as, say as in terms of HP in terms of in meters of water, minus H1, this height multiplied by the specific gravity or the specific weight of water, S water, and then this is the manometric liquid, minus H2 into the specific weight of oil, S into S oil, specific weight of oil, plus H3 the specific gravity, specific weight of water. So this is equal to HQ, the pressure at location Q in terms of meters of water. So now using this equation we can write HP minus, so this 300 millimeter 0.3 into 1 the specific weight of water, so 0.3 into 1 minus 0.2 into 0.9, the specific weight of the oil is given as 0.9 with respect to the water, 0.9 times of water. So 0.2 into 9 plus this is again this H3 is water, so 0.7 into 1 that gives HQ. So the pressure difference between P and Q is HP minus HQ is equal to minus 0.22 meter of water. So this can be we want to get in terms of Pascal. So P, the pressure difference in between P and Q can be written PP minus PQ is equal to this specific weight of water can be multiplied. So gamma into HP minus HQ. So this is gamma is equal to rho into G. So this is equal to 9806 Newton meter cube into minus 0.22. So this gives, this is equal to 2157.32 Pascal or 2.157 kilo Pascal. So this way, using a differential manometer we can determine the pressure difference between P and Q. So now we have seen, say using a manometer how we are measuring the pressure. whether it can be a simple manometer connecting to only one location, or it can be a differential manometer to find the pressure difference connecting on both limbs of the U-tube manometer, so that we get the pressure difference. And then we have seen inclined or tilted type of manometer, say, and then we have seen the advantages and disadvantages of manometer. So, as I mentioned earlier, this manometer, using manometer, the pressure measurement is cumbersome, since we have to measure the height and then use some equations to convert. So, nowadays we have this mechanical and electronic, say, equipments for measurement of pressure. So, the advantages of this mechanical and electronic pressure measurement equipments are, it is very fast, it is high pressure can be or low pressure can be measured, and rapidly varying or small fluctuation can be also obtained accurately. So, here in this slide you can see different kinds of mechanical. So, the on the left hand side you can see different kinds of mechanical type of these kinds of, say, the pressure measuring gauges, and this enlarged portion is, say, either it can be the electronic type is also shown here. So, what we are doing is we can just put this to particular location, and that is through some types of impulses it will directly give the value of the pressure as a Pascal or kilopascal or which unit we are looking for. And one of the most commonly used gauge for pressure measurement is called a Bowden gauge. So, here this figure shows the Bowden gauge. So, in the Bowden gauge, the pressure is measured, say, by using a, say, you can see here a hollow curved tube of gauge is, say, is used. So, this tube tends to straighten when there is a pressure. So, through a set of linkages, as you can see in this the Bowden gauge, through a set of linkages that is connected to here, so that a slight motion at end of tube that is translated into rotation of this dial here, and then that indicate the gauge pressure directly. So, that the directly this rotation is translated into the gauge pressure reading, and then we can directly get the reading. So, now instead of using the manometer or piezometric type say pressure measurement, nowadays we are generally using the pressure measurement using the mechanical or electronic type pressure gauging equipment like a Bowden gauge, as we have seen. So, now we will in detail discuss about the forces on submerged surfaces in static fluid. So, we have already seen some of the theories related to this. So, important features of static fluid which we have discussed so far is, see, the hydrostatic, first one is hydrostatic or vertical pressure distribution. So, we have already seen what is the hydrostatic pressure distribution. So, say if you consider a small basin or a tank of water like this. So, the hydrostatic pressure distribution, the linear pressure distribution we have already seen. So, that is one of the important feature which we will be using, and then the second one is pressure at any equal depths is in a continuous fluid are equal. So, say if you consider the fluid in this basin or container, so the pressure at any equal depths, say here if you consider here or this location or this location, pressure at equal depths in a continuous fluid are equal. And then the third important feature which we have discussed is Pascal law. So, according to the Pascal law, we have seen the pressure at any point acts equally in all directions, and then the last point is forces from a fluid on a boundary acts as right angle to that boundary. So, forces are acting at right angle to the boundary. So, this all important features we have already discussed. So, based upon these features, now we will be discussing the forces on submerged surfaces in static fluid. So, first let us consider, say, an inclined plane like this. So, forces, as we have seen, forces acting at right angle to the surface. So, the fluid pressure on a surface is obtained as F is equal to P into delta A. So, if you consider here, say here a small tank of water. So, then if you are considering a small inclined plane like this, then the pressure, say at various locations F1, F2 like that, we can, with respect to the slide, you can see there, say F1 is equal to P1 into, so here F1 is equal to P 1 into delta A1 and F2 is equal to P2 into delta A2. So, like that at various locations Fn is equal to Pn into delta An. So, that resultant force we can write the total force is equal resultant force is R is equal to P1 into delta A1 plus P2 into delta A2 plus P3 into delta A3 like that plus delta N delta An. So, this gives the resultant force, and generally as we discussed earlier, the resultant force acts through a center of pressure at right angle to the plane. So, with respect to this plane we can just find the center of pressure where the total resultant force is acting. So, the force on submerged surfaces we can determine like say the resultant force, and then we have determined the center of pressure. And then now we will see the forces on submerged surface fluid again say in a horizontal submerged plane. So, if you consider a small tank like this which we have already seen here, at the bottom say bottom we can say that it is the bottom is say horizontal. So, the resultant force is equal to, so the force on horizontal submerged plane pressure intensity P, it is equals at all points. So, that we can write resultant force R is equal to pressure into area of plane, or that is equal to P into A. So, if we consider atmospheric pressure as here as 0, then the resultant force in the case of a horizontal submerged plane is equal to small p into A. So, similarly we will consider now the resultant force and center of pressure on submerged inclined plane surface. So, here this inclined plane surface, say here you can see this is a tank of water, and then an inclined plane is considered like this, and now we want to determine the resultant force and center of pressure on submerged inclined plane surface. So, this we will be determining. So, this we will discuss in the next lecture.